Okay, we're going to use the previous problem as a jumping off point to discuss a little further the relationship between Darcy's law and pumping. We're going to get into some pumping equations next class. So what we're going to do today just sort of sets that all up. So the previous problem that we attempted, what I've done on this slide is I've put the pertinent data that I gave you in the previous problem. Remember, the aquifer thickness is 33 meters thick, and the width of the aquifer is 7 kilometers thick, or 7,000 meters. All right, so that's the size of the aquifer, 33 meters thick, 7,000 meters wide. And what we ultimately want to know is how much water is passing through this aquifer every day, past a certain point. So what we use is Darcy's law, which I've put right here. The flow rate through the aquifer equals negative K. K is the hydraulic conductivity, which is right here, 1.2 meters per day. A is the cross-sectional area, which is going to be 33 meters times 7,000 meters. This value right here is called the hydraulic gradient again. It's the slope of the total head in the aquifer. You can see that this well here is at 98 meters. Actually, I wrote that wrong from the previous example. This should be 97.5 meters. Let's get this exact. So 97.5. This one right here, 89 meters. So there's a gradient between well 1 and well 2. This well that's set back a little bit right here is 8.5 meters higher than this closer well, and the distance between those is 1.2 kilometer. So the DH is the change in head between two wells. And DL is the distance between the two wells. Change in distance. Okay, so we have our flow rate, some sort of volume per unit time. Typically, we will do this in meters cubed per second or cubic feet per second. In this case, I'm asking for it in cubic meters per day. Unit can vary, but it should be a volume divided by time equals the hydraulic conductivity, which varies from aquifer to aquifer, times the cross-sectional area. If you have a bigger area, more water is going to be able to move through it. That's why Q and A are directly related. And then times the hydraulic slope that we have right here. So again, this is the hydraulic gradient, hydraulic slope, you call it either way. Change in head between or over distance. So if you have a greater difference in the head, that's greater pressure differential. You end up with more driving pressure and greater flow. So you should be able to look at these equations and see how things are related. So when we punched in all of the different variables in the last question, we got a daily flow rate of almost 2,000 cubic meters per day flowing through that aquifer. Okay, so every day, if you were standing at a point on the surface and you had an aquifer beneath you, almost 2,000 cubic meters of water would pass below you, being pushed by a pressure differential, which is reflected in the head values of two wells that penetrate into it. Okay, so that's what we did for our last question. All right, so let's go on. I'm going to use this data and ask you a new question. We're going to continue on. So the next question, we'll have our previous question be A. We'll let this question be B. I'll simply ask you, we know the water is moving through the aquifer, almost 2,000 cubic meters per day. But another question we could ask ourselves is, how fast is the water moving? What is the velocity of groundwater movement through this aquifer? Now, if you look at the previous page of notes, one thing that I added to it in red was a grain size for the particles in the rock in the aquifer. We're going to use that here in a little bit. I think I put, let me look, what did I use for a value for that? I used 0.05 centimeters. So I think that's a sand size. I'd have to look it up to be sure. Okay, so with this question, what is the velocity of groundwater movement through the aquifer? Just to refresh your memory, in the previous example, we ended up calculating a flow rate of 1,964 meters cubed per day. And that's through 33 by 7,000 meter cross-section in your aquifer. That's how much water it passed per day. So the question I'm asking you now is, how fast is it moving? Well, we know that flow rate equals velocity times cross-sectional area. Remember, velocity we measure, in this case, it could be something like meters per second. Cross-sectional area, width times depth, or meters times meters. If you multiply this together, you get a volume over time, which is exactly what we want. So what we want to ultimately do is we want to solve for velocity in this case. So we know we have 1,964 cubic meters moving through this every day. We're going to solve for velocity. We know our cross-sectional area is 33 meters times 7,000 meters. Okay? There is one small adjustment we have to make, because remember, the water is not flowing through this entire area. I mean, that's the area of the aquifer, but most of the aquifer is rock, and the water isn't going to flow through the rock. The water is going to flow through the pores in the rock. And remember, I gave you a value earlier that we didn't actually use in the previous problem, that the effective porosity was 5%. So the water can only effectively move through 5% of this cross-sectional area. So we need to make an adjustment for that. So what we do is we have our 1,964 meters cubed per day. That's going to equal our velocity times our cross-sectional area. And if you multiply this out, you get 231,000 meters squared. But then we have to multiply it by the amount of openings, which is only 5% or 5/100ths of that aquifer. Now, if we rearrange to solve for velocity, we end up with 1,964 meters cubed per day over 231,000 times our 5%. Continue on with this. I'll rewrite this last part on the next slide. So our velocity equals 1,964 meters cubed per day divided by 231,000 meters squared, which is our cross-sectional area. But we're only moving water through 5% of that. And we end up with a velocity of 0.17 meters per day. So not very far per day. And as we've talked about, most groundwater moves pretty slow. So this would move about 2 decimeters in a day. If you want to change that to how much per second instead of per day, we can do that. We just need to do a conversion to get rid of day. So we have 1 day over 24 hours times 1 hour over 60 minutes times 1 minute over 60 seconds. Get rid of the day, we can get rid of the hour, we can get rid of the minute, and if you multiply this out, you end up with 2 times 10 to the minus 6 meters per second. A very slow groundwater movement. But because it's moving through such a large surface area, you actually end up with a pretty large amount of water, 1,964 cubic meters, flowing through this every day. Okay, so last class, I guess 2 classes ago, I said that whenever you use Darcy's law, you have to make sure Darcy's law is valid. And Darcy's law is only valid when the flow through the aquifer is laminar. So the question I have for you now is, Darcy's law valid for this situation? Now remember, we use something called the Reynolds number, which is rho, which is density of water, times the velocity of water, times d over viscosity. So again, rho equals density. Density for water we typically use as 1,000 kilograms per meter cubed. Velocity we typically use in meters per second. That's why I actually went ahead and changed the above value to meters per second, because we can use it in this example. D is the diameter of the opening. We'll come back to that, but remember last class I said this is actually kind of difficult to measure because, again, pores are so small. Then we have viscosity. The viscosity for water is 1.14 times 10 to the minus 3 grams per centimeter per second. Unfortunately, that means we're probably going to have to convert because we've got grams, kilograms, meters, centimeters all going on in this problem. And remember, and this is for open channel flow, if your Reynolds number is less than 2,000, then it's laminar. But remember, I also said that measuring this diameter of the opening is really, really difficult. If we change it from diameter of opening to grain size, then what happens is we take and adjust our Reynolds number. So anything less than 1 is laminar. All right. All right, so let's sort of plug this in and see what we can come up with. So again, our Reynolds number is density times velocity times diameter of the opening over viscosity. But if we change diameter of the opening to diameter of the grain size, then we need a Reynolds number that's less than 1. So we know our density is 1,000 kilograms per meter cubed times our velocity, which we calculated in the previous example, 2 times 10 to the minus 6 meters per second, times the diameter, which was 0.05 centimeters, which is 0.0005 meters. And then that's over the viscosity, which was 1.14 times 10 to the minus 3rd gram centimeter per second. Now you can see we've got grams, we have kilograms. We have different units going on, so we're going to have to convert one of these. So you can pick whatever one you want, but I'll change and convert this so that all of our units are consistent. So let's just do a little side light here and convert from gram centimeter second, and what we want to change it to is kilogram meter second, so that we can start crossing out some of our units and come up with a final answer. So if we start with 1.14 times 10 to the minus 3, let's get rid of our grams. We know that there's 1,000 grams in 1 kilogram. Okay, so we now have grams taken care of. We now want to get rid of centimeters and change it to meters. We know there's 100 centimeters in 1 meter. We can leave our seconds the same. So let's get rid of centimeters there. Okay, so we have 100 on the top right here, 1,000 down here. Means we're going to divide the whole thing by 10 ultimately. So we're going to end up with an answer of 1.14 times 10 to the minus 4th. It's 10 times less than the previous answer. And now we have a new unit, kilogram meter second. So if we turn around and plug that in here, do our math, we end up with an answer that is 8.8 times 10 to the minus 3. Remember, Reynolds number, all the units cancel out. We have a kilogram here. It'll cancel out with that. Meters cubed here. Meters 2, meters 1. So we have a per meter up here. Cancel that out with the per meter down here, and then we have the seconds that will also cancel out as well. So we should end up with a dimensionless number. In this case, it is less than 1, much less than 1. So Darcy's law is valid. So your answer should have some grounding in reality. Okay, one more question I'm going to ask you. This goes back to one part of this problem. I'd like to know what is the height of the potentiometric surface Remember, that's the total head value. At a point that is 0.3 kilometers from well 1 and 0.9 kilometers from well 2. So go back and look at the previous problem and see if you can figure this out. I'll give you a minute or so. Remember, the total head value for well 1 was 97.5 meters. Total head value for well 2 was 89 meters. And these were 1.2 kilometers apart. So see if you can figure out what the total head value would be at a point that is 0.3 kilometers from well 1 and 0.9 kilometers from well 2. If you want to kind of think of this in profile, you could do a little triangle like this where here's well 1, 97.5 meters. Here's well 2, 89 meters. So this would be well 1. This would be well 2. In this case, you're going to be 0.3 kilometers from well 1 and 0.9 kilometers from well 2. So I basically want to know what is that height right there. So perhaps this is a landowner that lives between the two wells and wants to drill down and wants to have some idea of, how far down is the water going to rise up in my well. So see if you can figure this out from the information I've given you. All the information you need is basically right here. So I'll give you a couple minutes to go through that. Okay, if you're not ready to move forward, you can pause the video, but let's go through this. Now, there's actually a number of ways that you can do this problem. For me, probably the easiest is to simply figure out the slope of this line, which is pretty simple. Okay, so that is the slope of the potentiometric surface. You could do this with trig as well. Should get the same answer. Also known here as the hydraulic gradient. It's how much the head drops per unit distance. We know the total distance between well 1 and well 2 is 1.2 kilometers. And we know that the head drops by 8.5 meters over that distance. So 97.5 minus 89, that's our drop in head over our distance between, which is 1,200 meters. That's 8.5 meters divided by 1,200 meters. And if you calculate that out, you get a drop of 7.08 meters per kilometer. Okay, so that's how much this slope changes from well 1 to well 2. Well, since we have a slope, 0.8, and we want to know how much is going to drop over the next 0.3 kilometers, we can simply multiply that. 7.8 times 0.03 kilometers. Kilometers are going to cancel, and it's going to drop 2.12 meters. So from this point right here to this point right here, it's going to drop 2.12 meters. Well, if we start out at 97.5 meters, and subtract 2.12 meters, we should end up with a total head value of 95.4 meters. It obviously shouldn't be higher than 97, shouldn't be lower than 89. The value should be between those two. 97.5 is between those two. 97 or 95. Wow, I'm having a hard time talking here, sorry. So our value right here of 95.4 meters should be between 97.5 and 89 meters, and it is. So that would be the head value at a point 0.3 kilometers from well 1 and 0.9 kilometers from well 2. Okay, so again, if you're having issues calculating these quantities, let me know, and I can come up with some more practice problems for you. Okay, that's all we will have this week. Next week, we're going to look at pumping. We're going to look at cones of depression and things called capture zones, and that's going to be our final chapter, final set of topics that we'll go through this semester. So you're getting close to the end, and we'll discuss the final next week as well, because that's now rapidly approaching. So make sure you get your homework done. Don't delay on that, because you got your other classes, and even if this is your only class, we're going to have a final, and obviously covers quite a bit of material. So you don't want your final homework to cut into your study time for your final exam. So get at that, get it done, and the earlier you get to it, if you get stuck or have questions, then you have time to meet with me and work with me on it. Okay, that's all for today, and I will see the face-to-face students next week. Online students, keep communicating with me and let me know how you're doing. Okay, see you all soon.